Okay, hi, I'm Alina Tovar, and this is my Lab 2 over projectile motion. So, the purpose of this lab is that we wanted to capture the forces acting on an object moving in projectile motion, and then we wanted to create a computational model both with drag and without. Without drag, it would just be the gravity force, and then we're going to compare the graphs. So, a preview of the results is that we found that when we added more forces acting on the object, our predicted data became more similar to the observed data. So, this just means that when we added drag force to our net force, rather than it just being gravity, then our computational model became more similar to what we observed. So, the physics principles, models, and assumptions that we used for this project, one of them is Newton's second law, which is that the net external force equals the change momentum of a system divided by the time over which it changes. This is the momentum principle. And then for this project, our system was the marker cap that we used that was moving in a projectile motion, and then the surroundings is Earth and the drag force. So on the right, we have the equations for both of the forces acting on the system. And then we also have the velocity and position update formula. And just as a reminder, velocity will not change if the net force is equal to 0. So our experiment setup is that we had to record a video of an object. We used a marker cap that was being thrown upward and making an arching shape. And then we used Tracker to track the position of the object through time. And then we went over to our code in GlowScript to create a computational model of the predicted position. And then we compared all of our graphs in Google Sheets to see the difference between our predicted and observed positions over time. And then down below, we just have the initial conditions, including the initial time, position, and velocities. Position and velocity are vectors, so you can see that there was motion in the x and y direction since it's projectile. So using Tracker, the little triangles show how I manually inputted each different position over a certain amount of time. And then to right, you have a preview of our graphs and then what we recorded for our x, y, and then initial xy velocity, position, and velocity. So then our coding, this is the coding that we do not have any drag. So we started with a mass of 0.001, and then we added our initial conditions that we calculated. And then our drag is 0 because we were only looking at the gravity. And then we changed our error scales to update that. And then you can see our graph that we got from this code on the left. And then coding with drag, the only things that we changed is that we added the drag force to the net force, which was originally just the gravity force. And then we changed the drag at the bottom to 0.01. So there wasn't much drag on this, and it gave us about the same kind of graph. So when we compared our models in Excel, you can see that they are very, very similar. And since our object was very small and didn't have much mass, then the drag force didn't really affect it much. But you can see that it is closer to the observed motion when drag force is included because it's taking into account more forces that were acting on the object. Now, possible errors for this graph is that there may have been a human error when manually tracking each position, and then we also had to estimate our drag force and the mass of the object. So then we have terminal velocity, which basically is just when a free-falling object experiences zero net force. And since our object was so small that it didn't really experience this terminal velocity, but in a future experiment to determine the terminal velocity, we could include a larger object falling from a higher distance, and this would change this kind of velocity time graph. It would change it so that it would even out at the bottom and eventually experience the terminal velocity. So, what if the object was thrown straight up? So, if would the time it takes to reach the ground be different? If the object was thrown straight up with the same initial speed, it would take longer to reach the ground. And this is because at the time of flight for a projectile, it depends on the y component of velocity, which is smaller than the initial velocity. And to the right, we kind of have the mathematical or like equation side of this proving that this is true. Thank you for watching my presentation.